All right, chapter 3 talks about structure of matter and the chemical elements. Now, we came across the definition of matter, probably in the previous chapter. Matter is anything that does have mass and occupies volume, occupies space. So anything that does have mass and volume, it will be labeled matter. So this chapter talks about a very important concept, that is kinetic molecular theory. What is the kinetic molecular theory? Kinetic molecular theory, it explains the difference between the three different states: solid, liquid, gas states. So all of these, regardless what states we're talking about, we know that all matter composed of tiny particles. And these tiny particles are always in constant motion. And these particles that are moving in constant motion, that motion will be increased if the temperature is increased. This is something that is common between the three. However, solids, liquids, and gases, they differ in the freedom of motion of their particles and how they are attracted to each other, due to the, once again, to the way how the arrangement of those particles within the solid, liquid, or gas states. And this is what I want to explain next. How, in brief, how is it really the gaseous matter versus solid versus liquid look like within that matter? Let's agree one more time that all matter, regardless what state we have, they composed of tiny particles, and these tiny particles are always moving. And this motion will be increased if the temperature is increased. This is something common between the three states. All right, the difference between solid, liquids, and gases. Solid, when you look at the atoms, or when you look at the particles within the solid phase, there's not much space between them. These particles are intact. They're right on top of each other, next to each other. You could see here, here's an example where you see the particles are very, very close to each other. There's not much, there's no space even between them. And that explains why the motion is very limited. The particles are not moving at all. And here's the proof. If I give you like a solid object, and this solid object, you're trying to place it inside a glassware container. If this solid object doesn't fit into the glass container, it will not get in. It will not change its volume. It will not change its space. What will it occupy? Why? Because this solid has particles that are very intact, and the shape is fixed. So not just the volume is fixed, the shape is also fixed, due to the nature of the particles within this matter that are very close to each other. And the attraction is very strong. So no space between the particles, and the attraction is very strong. That's why volume and shape are fixed. While liquids, there is some space between the particles that will allow the motion to be a little more compared to the solid phase, and that gives it to be fixed volume but variable shape. What is that supposed to mean? Variable shape, fixed volume. If I give you a bottle of water and I tell you, all right, fill it up in this beaker or fill it up in the other container, the volume will still be the same that you're delivering. You're probably going to be delivering like 250 milliliter. And that 250 milliliter will be the same 250 milliliter in the other container that you delivered it to. However, this shape of liquid in the water bottle may not be the same shape of the mug that you probably delivered the water to. So that's what we mean by variable shape, but fixed volume. The variable shape for liquids, it's something that is controlled by the glassware that you are placing it in. But the fixed volume is due to the fact that you have, once again, the mass and volume of that matter that you are dealing with. It will not change if the conditions are not changed. Moving on to the gaseous phase. Gaseous molecules, the space between the particles are huge. And the reason behind that is because of the weak attraction between the particles. So large distance between particles, little attraction between them, that will give the gaseous matter to be in variable shape and variable volume. It's like when you have a balloon. You fill up the balloon with helium. You take that helium and you deliver it into a container. That container could be a rectangular object, a rectangular like shaped container. You take that and you fill it up. So that's a variable shape. And what we mean by variable volume, think of the propane tank. When you want to grill and you're grabbing that propane tank, you can't tell if it does have half of it or if it, unless there is a measuring device that's on top of the container. What I'm trying to say here, the propane, when it's inside the container, it could fill up the entire space, even though it's not more than half of that space. That's what's worth. Meaning, I could have half of that tank is what I really have, but this half is not really just filled with one half. It's filled up the whole container, the whole space, because that's the tendency of the gaseous molecules. They like to be as far farther apart from each other as possible due to the weak attraction between them. So the take-home message out of the kinetic molecular theory is, once again, that all matter composed of tiny particles, they move all the time, and this motion can be increased if temperature is increased. When it comes to the states of matter, they can be solid, liquid, or gas. Solid, distance between the particles is very small. They are intact. That will give them fixed volume, fixed shape. Liquids, there will always be some space between the particles. The motion is more free compared to the solid phase, and that will give them fixed volume, variable shape. Fixed volume, variable shape. Moving into the gaseous molecule, to the gaseous phase, the distance between the particles is always huge due to the weak attraction between the particles, and that's why the shape and volume are always variable for any gaseous matter. Periodic table consists of groups that are columns and rows that are periods. So you got the groups going from top to bottom, and you got the periods going from left to right. So you could see here you have 1A, 2A, 3B, 4B, all the way to 3A, all the way to 8A. These are groups. When you have also 1, 2, 3, 4, 5, 6, 7, these are periods. So I have 7 periods total. I have 18 groups total. 18 groups total, and I have 7 periods. What else do I need to know? I need to know that some of these groups, they have names. For example, group 1. Group 1 is referred to as alkali metals. So when I see lithium, sodium, potassium, rubidium, cesium, francium, these are all belong to the same group of alkali metals. Second group, going from beryllium all the way to radon. So these are elements. They all belong to the alkaline earth metals. Alkaline earth metals. I don't necessarily I'm not required to know properties of those. I don't need to worry about those. Later on, we're going to learn some of the chemical behavior, how they behave in chemical reactions. That's what's more required than knowing what properties they have. You got group 17, which is halogens, going from fluorine all the way to astatine. And you have the last group, which is 18, noble gases. These are basically going from helium all the way to radon. So these are the noble gases. It's important that we able to recognize what these groups are, because I could be asking you the question, which of the following is an alkaline earth metal? Which of the following is a noble gas? So if you wouldn't know where the groups are in the periodic table, obviously you will miss a silly question like that. Another classification that's important to know, that you have metals and non-metals. The metals usually are to the left-hand side of the periodic table, and the non-metals are to the right-hand side of the periodic table. And these two groups are usually separated by what we call metalloids. Metalloids, going from boron all the way to astatine. So you have boron, silicon, germanium, arsenic, antimony, beryllium, and astatine. All of these are metalloids, meaning they share the two groups' properties, metals and non-metals. And once again, I'm not going to be asking you to list properties of metalloids. I will not be asking you to list properties of metals, but it's important to know where the metals are and where the non-metals are. Two more groups to know: transition metals, which is basically the 10 groups right here, 3B all the way to, 3B all the way to 2B, 3 to 12. This is the transition metals block. This is the transition metals. So you got period 4, 5, 6, and 7. This block, which consists of 10 elements per row, you got 3 to 12, that's 10. And underneath it, you have what we call the inner transition metals. The inner transition metals. So this is something important to also keep in mind, because I could be asking you once again a multiple choice question telling you to tell me which of the following doesn't belong to this group and which of the following is an element of that group. Okay, I wouldn't worry much about knowing which one is in a solid phase, which one is a liquid phase, but I could just brief this in one sentence. Elements on the left-hand side, they tend to be solid. Elements on the right-hand side, they tend to be gaseous. Meaning, if I'm dealing with oxygen, the fact it's on the right-hand side, I wouldn't expect it to be in the solid form. If I'm dealing with sodium, I would expect it to be in the solid phase. So that's the difference between the left-hand side elements and the right-hand side elements. So you always go from solids to the left, go all the way to gaseous to the right, passing by liquids in the middle. All right. What I want to talk about next, something we call it atomic theory. Atomic theory, it tells me since we just said matter consists of particles, tiny particles, these tiny particles, they are referred to as atoms. And atoms, researchers, they spent a lot of time trying to understand what's within the atom and what do they all consist of. And I don't want to give you the history. I mean, you could read about it, but what's more important is to understand the final version of this atomic theory that tells me what does atom have inside of it. So the atom, which is about 10 to the negative 10 meter in size, it's actually consists of subatomic particles. These subatomic particles, we refer to them as neutrons, protons, electrons. And the way how these subatomic particles located inside the atom is as the following. You got a nucleus, the nucleus within the atom, which is the positive part. And why is it positive? Because it does have the protons that are positively charged. And outside the nucleus, you got the electrons floating around. The electrons are negatively charged. They are outside the nucleus. And you got the third subatomic particle that gives the mass of the atom. So those elements, they do have mass. And that mass comes from the neutrons. Neutrons are neutral. They have no charge, but they are the ones that actually contribute to the mass of the elements. Where are they inside the atom? They are inside the nucleus. So the final version then of this atomic theory, that the atom is a spherical shaped body, does have a positive part, that's the nucleus, consists of protons and neutrons, and electrons are floating around the nucleus inside the atom. Let me see if there is a, yeah, unfortunately, it doesn't have, yeah, I guess here it shows you basically that the nucleus does have the proton and neutron, and the electrons are floating around the nucleus. So this is just a carbon atom. Shows, this slide shows what does the atom of anything usually consist of. So this is the atomic theory. That is the most agreed upon theory that tells us what the atoms do have inside of them. So once again, protons, neutrons, and electrons are subatomic particles. Some are positively charged, which are the protons. Some are negatively charged, which are the electrons. And you got the neutrons are neutral. They are zero charge. What are they for? They've been found that these neutrons are actually the ones behind the mass of the atom. The mass of the atom. All right. And that basically takes me to what we call ions. Ions are basically particles that could have more protons than electrons or more electrons than protons. In real world, in a perfect world, the element that's inside the periodic table, that is basically a symbol that doesn't have a charge on top of it, will assume right away that the protons and electrons are the same. Meaning, if I look at any of these elements, like let's say potassium. Potassium, I know right away that does have, because it doesn't have a charge on top of it, that the protons and electrons are the same. Neon, helium, nitrogen, all of these elements that are in this periodic table. But what happens if I have more protons than electrons? What if I have more electrons than protons? That's when we gonna produce what we call ions. So ions are basically charged particles due to loss or gain of electrons. If the element does lose an electron, automatically will carry a plus charge. And this plus charge, basically due to the loss of those electrons, because you have now more protons than electrons. So once again, if you have an element that loses an electron, that means it's going to carry a plus charge due to the fact that it's going to be more protons than electrons. And that's why it'll become cations. So cations are basically positively charged ions, positively charged particles. The opposite to this is when you have an element that gains electrons. That means you're going to have more electrons than protons. And that's why they become anions. They're going to carry a negative charge due to the fact that you have more electrons than protons. So those elements that we see in the periodic table, they are neutral due to the fact protons equal electrons. But the moment that an element loses an electron or gains an electron, it will not be neutral anymore. If it loses an electron, it will carry a plus charge. If it loses 2 electrons, it will carry a 2 plus charge. If it loses 3 electrons, it will carry a 3 plus charge. These will be referred to as cations. The opposite to this, if you have an element that gains an electron, then it will carry a minus charge. If it gains 2 electrons, it will carry a minus 2. If it gains 3 electrons, it will carry a minus 3, and so on. And these will be referred to as anions. So cations and anions are basically charged. So any of those elements that you see in front of you on this periodic table, you will notice that there are 2 numbers around it. Like for example, lithium has a 3 and it has a 6.941. Copper has a 29 and has a 63.55 around it. Phosphorus has 15 and 30.97. What are these 2 numbers? It's important to know what each of these 2 numbers mean. So if I take, for example, beryllium, I have 4 and 9. What's 4 and what is 9? The smaller number is always referred to as the atomic number. Atomic number. It's like the sequence of that element in the periodic table. It shows up in spot number 4. So its atomic number is number 4. And the larger number is always referred to as the atomic mass. So 1, which is the smaller, is the atomic number, and 1, which is the larger, is the atomic mass. I may come across a periodic table that will reverse them the other way around, having the 9 on top and 4 on the bottom. That doesn't change what each one means. I still gonna have the smaller number means the atomic number, and the larger number means the atomic mass. Okay. Yesterday we talked about the atomic theory, stating that the atom is a spherical shaped body. It has a positive part in it, that is the nucleus. And what's within the nucleus? I get the protons and neutrons. And what's outside the nucleus? I have the electrons surrounding the nucleus, floating around the nucleus within the atom. From these two numbers, I can tell how many protons, how many electrons, and how many neutrons I have. What is that supposed to mean? Back to the beryllium example. Atomic number equals 4. Atomic number is always equal to the number of protons. So if I say, what's the number of protons of copper? You will say 29. What's the number of protons of barium? It's 56. What's the number of protons of potassium? It's 19. It's always the smaller number. And if the element is neutral, that number will always equal to the number of electrons as well. So beryllium doesn't only have 4 protons, also have 4 electrons. So the positive cancels out the negative, and that's why you have a neutral atom. Lithium has 3 protons and 3 electrons. Zinc has 30 protons, 30 electrons. So it's important that we understand that every single neutral element, the number of protons should equal the number of electrons. They cancel each other out, and that's why the atom becomes neutral. What if zinc is carrying a +1? What is that supposed to mean? That means zinc lost 1 electron. What if zinc is carrying a 2+? A 2+, that means it lost 2 electrons. What if oxygen carrying a 2-? That means it gained 2 electrons. That means it has now 8 protons and 10 electrons. Protons will never change. Electrons will. So when atoms combine with other atoms, electrons that do change, whether they get gained or lost, not the protons. So protons, keep in mind that they will never change no matter what. Okay, so back to the point of saying cations versus anions. Cations will always have the number of electrons less than what it's supposed to have, which is supposed to be the number of protons for that element. Anions will always have more than the number of electrons that's supposed to be for a neutral element of that exact atom. So calcium, for example. Calcium, if it's carrying a 2+, what is that supposed to mean? What it means, it has 20 protons and it has 18 electrons because it's carrying a 2+. All right, so that's the atomic number. The larger number, which we just talked about, that refers to the atomic mass. What does atomic mass mean? It's the mass of the atom. How much weight does this atom have? Well, this atomic mass, we talked about this yesterday. One of the subatomic particles, which is the neutrons, is usually the one that contributes to the mass of the atom. How do I get the number of neutrons from the atomic mass? Is it 9? No. When you subtract atomic number from the atomic mass, that outcome is the number of neutrons. So 9 minus 4, which is 5, that's the number of neutrons in beryllium. 65 minus 30, 35, that's the number of neutrons in zinc. 108 minus 47, again, that's the number of neutrons in silver. So every single time you subtract atomic number from atomic mass, that will give you the number of neutrons. That's what it is when it comes to protons versus neutrons versus electrons. And it's very important that we are able to do this for any atom. So once again, let me brief it. Every single atom in the periodic table does have two numbers. A smaller number is the atomic number, a larger number is the atomic mass. Atomic number equals number of protons and will always equal the number of electrons if it is neutral. The number of neutrons equals atomic mass minus atomic number. The word isotopes always refer to the same atom exists in more than one spot on Earth, and that atom weighs different depending on the spot that's coming from. What is that supposed to mean? What it means, if I have, for example, an element that is, let me just come here. So let me see, there's one that is, it's supposed to be one right here, perfect. Here's an example, carbon atom. Carbon atom, it exists in two different masses. One that is 12 and one that is 13. That's how nature, I mean, you cannot explain nature all the time. I mean, some examples in nature will just blow your mind and say, wow. This is an example where you have an element that its atomic number is the same, but the atomic mass is different. One is 12, exists in 98.90% abundance, and one 13 unit, and that exists in 1.10% abundance. So for researchers, in order for them to come up with an average atomic mass, they don't just add up these two numbers and you divide it by 2. You cannot do that. I mean, you don't do just the average atomic mass by adding up the two masses and you divide them by 2, because the percentages are not even. So what do you do then? What you do instead, this percent, you convert it back to fraction. How do you convert a percent back to fraction? You divide it by 100. And when you divide 98.90 by 100, you get 0.989. And when you divide 1.10 by 100, you get 0.0110. So that's the step number 1. You get that percentage converted back to fraction. Then what? You time each fraction by the atomic mass of that isotope. You time the fraction by once again, by the mass of that atom, and this outcome, you add them up at the end, and that outcome is the average atomic mass of the element that you see in the periodic table. Once again, those atoms that exist in the periodic table do have atomic masses already plugged in those periodic tables. Where did this atomic mass come from? Came from a method that is the calculation of average atomic mass. How do you calculate the average atomic mass? Those researchers will look for where does this element exist on Earth and how much it exists in terms of percentages. So they start looking for sources of those elements where it exists on Earth. And every single time they find it, they will basically apply a method to find the mass. And once they find the mass, they will be able to basically find out the percentages of that element in that mass, in that sample. So here is carbon, for example. It exists in two different masses. And we already know the atomic mass, what changes it is the number of neutrons. So these two samples, they basically represent the same atom, which is carbon. And these two different masses indicate I have two different isotopes for carbon because it has two different masses. So every single time you hear of the word isotopes, you should link it right away to the number of neutrons. Means I have two atoms of the same, but two different atomic masses. All right. How do you calculate the average atomic mass? You get the percentage, convert it to fraction, you time it by its mass, and then you add them up. And the add up will give you always the average atomic mass, what you see on the periodic table. So this is an important method that we need to be aware of, how to do it. In case of I'm given a question, I have 3 isotopes, and each one has a percentage and has a mass. What do? You get the percentage back to fraction, you time it by its mass. Once you do that for the 3 different isotopes, you add up the numbers, and the outcome would be the average atomic mass. That's the story of atomic mass. Next will be the concept of mole. The word mole, what does it mean? It's a unit used to indicate an amount of substance. And this amount of substance, which is 1 mole, will always have the same number of the smallest particles exist in that substance. And we learned yesterday from the modern atomic theory and the kinetic molecular theory, we said that the smallest particles in the element is the atoms. And we said atoms, usually, they have within them protons, neutrons, and electrons. So we know that the smallest thing in the element is the atom. Now, what's been found that 1 mole, which is an amount of substance, of any of those elements will always equal the same number of atoms. And what is that number of atoms? Is the 6.022 times 10 to the 23rd, which is referred to today as Avogadro's number. So what is Avogadro's number? Avogadro's number indicates that set amount of substance of any source, of any kind, will always equal the same number of atoms. And that is 6.022 times 10 to the 23rd. So if I take 1 mole of carbon, which weighs 12.011 gram based on the periodic table. If I take 1 mole of magnesium, which weighs 24. So if I take oxygen, which weighs 15.9, any of these elements will always have the same number of atoms of that element, which is 6.022 times 10 to the 23rd. That's Avogadro's number. So in this chapter, there is not much calculation will be required from you in regard to how to go from mole to gram, or gram to atomic mass, or atomic mass back to moles. That will be delayed until after, until a later chapter, actually. So it will be combined with a different chapter. But what's more important for you to know here is to know what each one means. What does atomic mass mean? How do I calculate it? What does mole mean? What does Avogadro's number mean? These are very important to keep in mind. So let me end the talk with knowing that every single element is going to have a mass, and this atomic mass already exists in the periodic table, and this atomic mass comes from a method that is called the average atomic mass method, by considering the isotopes of that element on Earth. And I'm going to skip all that. That's not going to be something that you need to worry about in this chapter.